Okay, extending from the previous one, just note some things have changed here, including here, I've got voters and non-voters. This is now hypothetical. I'm using the same outcomes and sample sizes as before, and we'll say that they belong to Gallup and Rasmussen, and so they're not just different samples, they're different, we call the measurement setup, they're different preparations. But we're just going to treat them as two different samples and wonder about the prospect of one being equal to the other in repeated samples. So there's define a very important sort of standard of normal frequentist probability and inference called the p-value, which is, I'm working with proportions here. Distinguish those sample proportions from the p-value, which is about to come. So you can do the same thing, I will, with sample means x bars, where the data are not dichotomous variables, but instead ratio level variables. So we've got non-voters from Rasmussen and voters from Gallup, and I'm going to have the following null hypothesis that p hat g, this is p hat g and p hat r, I know those are small, that they're equal, so in repeated samples. And this null hypothesis assumes that we have different scores, 0.44 and 0.48, simply by chance and due to sampling error, and that if we kept on and on and on and on observing from both houses, we would find something roughly equal at the end. And the alternative hypothesis is that they're not equal. You'd know the direction because you can see it. The Rasmussen value is higher than the Gallup value, and the Rasmussen value, as we saw last time, has attached to it a confidence interval that encompasses 0.5, the 50% mark. Now we're asking whether these things are different by sampling error, different by chance, or instead, if we can find some security, looking across samples and say that there seems to be evidence favoring the alternative hypothesis here. So you got another, this is another z, and to cut to the chase right here, it's just the difference between two sample proportions, given a few assumptions. The difference between two sample proportions is also distributed normally in repeated samples in the same way that each one of them are. Instead of just adding a layer, I'm using proportions here because the arithmetic is very simple. This may strike you as complicated, but if I use sample means from ratio level variables, it would be more cluttering, but this is just the difference between the two scores. This could be equal to 0.04, right? And you're dividing 0.04 to find a single standard error. This would be z across repeated samples. We're going to find a single standard error for the sample proportion. These are the combined data. So you add both of them up, all the zeros and ones from both, and all the zeros and ones from the other. You would normally have to weight these. I have identical sample sizes so that the problem simplifies a little bit. So it'd be 0.44 and 0.48. It'd be the point right directly in between them. Would be p bar, and then 1 minus p bar, and then I'm dividing by the sum of the two sample sizes. That would be 3,000, and taking the square root of that, and finding the z-score. And it's the z-score is minus 0.22, 2.2 rather, minus 2.2. So it's way more negative. Way from beyond the 1 standard deviation. It's 2.2 standard deviations or standard errors. And so we're going to look at the area of the curve, like right here. Out to 2.2, leaving space in the tails, and wonder about the percentage of area under the curve that seems to be excluded by this. This is 0, which would mean no difference at all. We've got a z-score here of 2.2. It has an exact p-value associated with it. And I believe it's 0.0 0.028 0.028, and 0.028 is underneath the magical, mystical 0.05. Bayesians are already up at arms. Underneath the magical, mystical 0.05 mark, which is the p-value associated with, for the frequentist, for no reason other than sort of tradition, almost arbitrarily. It's the p-value where if you go below, you say this difference is statistically significant. And so I've already have the Bayesians would be up at arms, but this is in fact the way frequentist inference is done. So I'm able to exclude all these over here. If I had a directional hypothesis, the p-value would be even lower because I'm including some area back over here. And statistical significance. So we want to know if there's a difference between the two, and if there is, we want to subsequently say whether it's a difference that we would observe over and over and over, repeatedly sampling from these two supposedly independent populations, non-voters on the one hand and voters on the other. And in this case, we find a statistically significant result that the 0.44 and the 0.48, given that we have sample sizes of 1,500 apiece, so total down here of 3,000, given such gigantic numbers, we're finding a statistically significant result in the parlance of the frequentist tradition of 0.028 for the p-value, and it's underneath 0.05. If it had been 0.057, then it wouldn't have met the magical standard. And yet still, at 0.057, we'd be able to exclude almost 95% of the possible observations of the differences on the proportion. This is it. This is frequentist inference. We are saying we want a p-value underneath 0.05. There, among frequentists are controversies about the p-value and how it's used, where it came from, how it's attached to sort of the balance of potential errors, and I want to introduce some new terminology. About inferential errors of type 1 and type 2. There are only two things possible here. That we say this difference is statistically significant, that's one, or that we say it's not statistically significant, and that the null hypothesis seems more plausible. Only two possibilities means that there are only two kinds of mistakes that we can make. On the type 1 error, we will be type 1 inference error is to say that is to find information favorable to HA. If you find information favorable to HA, the alternative hypothesis, and in fact the null hypothesis was correct. If you'd had all the data, you would have discovered that those tiny little areas outside that you excluded actually contains the correct value, or actually in this case, in the interior. So type 1 error is saying that there was a statistically significant difference when in fact there was not. And this is favoring the null. Favoring HO, if you find evidence that suggested these two parameters were not statistically significant, or the difference between them was not, and you go with that, and it's wrong, it's a type 2 error. Now this is hard, and people get it backwards all the time. So I want to say it one more time. To sort of get the first distinction, figure out whether you're saying you favor the alternative hypothesis, or on the other hand, favor the null. You'll already then be able to answer a test question about this, because if you favor the alternative hypothesis, or if you're data to, as was the case right here. So we found something statistically significant at a level less than 0.05 p-value. So we find here, we say there is a difference. The type 1 error is when you say there is, and in fact there isn't. If you had all of the data, you would come to the other conclusion. Type 2 error, exactly the opposite. That's where if you had found a statistically insignificant result, supposedly we had a p-value here of 0.36. We would say that's statistically not a significant result. We would then say then the null hypothesis cannot be rejected. We have evidence favoring the null hypothesis, and in that case the only mistake we can make is the circumstance when you have in the population there really was a difference, and you concluded here from the data that there were not. You can also think, and it's helped me, of type 2 error is throwing the baby out with the bathwater, concluding you sort of by definition sort of favor the alternative hypothesis, or you wouldn't have proposed it in general. And when you conclude that the idea that you had about how the data would fall out is incorrect relative to the null, you can throw the baby out with the bathwater by being strict here at 0.05 as opposed to increasing the standard. Now, notable before we move on, 1,500 in each. 1,500. These are large samples. These are large samples, and you have a lot of what's known as statistical leverage. Remember, recall, or look on your notes. You're dividing through by the sum of 1,500 plus 1,500. You're dividing through by 3,000, so you're making the standard errors very small. They are proportionate, remember, to the square root of the sample size. So they're going to go down. And if we translate this problem, so I'm going to in the subsequent video, into an experimental circumstance, we're going to think of what here is the distinction between voters and non-voters as a treatment variable, and go sort of think in quasi-experimental terms. Did the treatment seem to make a difference? That's quasi-experimental because we didn't make the assignment randomly from to one group and the other. But I'm going to translate this language and this idea into the laboratory, and in the subsequent video talk about, in the introduction to days, talk about p-values in a particular circumstance that was very prominent last year, the last time I taught this course. Forthcoming in a major social psychology journal was a study indicating that under certain conditions, or given a treatment, that students at Cornell University exhibited extrasensory perception. So talk about that in the subsequent video, then introduce Reverend Thomas Bayes, who has a different idea about how inference ought to work.